Hi, this is going to be an example of solving manometer problem. So this is a multi-fluid, as you can see here. Let's see what we got. So this manometer has this hydrogen gas here. This side also has a hydrogen gas, and it's two different pressure. Then the manometer have three fluids, and you have fluid A, B, C. They give us the density of each, and they also give us the height difference, H1, 2, 3. And they said the absolute pressure P1. So they give us the absolute pressure. P1 is here given 65 kilopascal. Okay, watch out for the unit. It's kilopascal. And they want us to find what's going to be the pressure at P2. Remember in the previous video on manometer concept, we said we start with something we know. And here is obvious, P1 is known. So P1 is 65 kilopascal. Then we go from there. We start our thread there. So if we know P1, I'm going to go ahead and label a few numbers on those points. For example, here I'm going to call this, since 1 and 2 are both used, I'm going to just call this 3. This is point 3. Then following this liquid, we get into right here. So we're going to call this point 4. Then we're going to go through another fluid, and this is going to be our point 5. Then the last fluid, we're going to from 5 to 6. This point called 6. All right, so now let's go. So if you know P1 already, what do you think the pressure at 3 will be? What's the pressure here? Well, over here, it's all this gas. Remember we're talking about the gas? No, regardless of the location, it's pretty much the same. The pressure is negligible in case you have hot air balloon situation. So P3 is going to take up the pressure of P1. So we know P3 now. Then we go through the first liquid, 3 to 4 here. So 4 compared to 3, they are the same liquid. So 4 compared to 3, it's going to be in higher location. 4 is a higher location. If it's a higher location, the pressure is actually lower, right? Because when you go deeper, the pressure go up. So P4 is going to be less than P3. How much less? It's going to be rho GH. And this rho is fluid A, so it's rho A, G. And the height difference between 4 and 3 is what? It's not H1, it's actually H2. That's a height difference between 3 and 4, so H2. Okay, so now we even figure out the pressure at 4 now. Then we just need to figure out the pressure at 5. So P5, they are going through the same bend, same fluid. And ironically, 4 and 5, you notice, it's at the same height. If the same height, you're going to have the same pressure. So P5 is going to be equal to P4. Well, that's easy. That's no hanging fruit. Now we're going to go to the last fluid, which is this green fluid here. And we are trying to figure out P6. Since now we know P5, and point 6 is located deeper than 5. Since it's deeper, you're going to have a higher pressure. So it's going to be rho GH. And the rho here is fluid C, so it's rho C, G, the height difference. So what's going to be the height difference here between 5 and 6? It's going to be here. Do we have that information readily available? Yeah, we have H2 here, and we also have H3 here. So the difference, H2 minus H3, is going to be giving us the height difference right here, right? Between 5 and 6. So knowing that, we figure out the pressure at point 6 right here. Our ultimate goal is to find the pressure P2. And P2 is gas here again. So we know P2 is going to take up the pressure at 6 because, again, it's gas, and the gas, the pressure at 6, and right here, it's pretty much the same. Then you got your answer for this problem. And if you look back, you realize you used liquid fluid A density. You also used the density of C, but fluid B we didn't use. The reasons for that is 4 and 5 outside the same height, so we will not use density at B here. So that's going to be a noisemaker here for this number right here. Okay, so put them together. Then you can combine them to figure out the pressure at 2 equal to what? So then let's see, P6. Let's combine them together for this problem. P6 is what we are, P2, sorry. So P2 is what we are solving. It's going to be equal to P6. And so let's bring it all in. And P3 is going to be 65 kilopascal. Then 65 minus this term, rho A, G, H2. That's your P4 now. This is going to be your P4. And this is going to also be equal to P5. Then P5 plus this term, rho C, G, H2 minus H3. That's going to be your P6. P6 happen to be equal to P2. So that's going to be our combined solution to find P2. One last thing I'm going to look at is the unit. So here, be aware, 65 is in kilopascal. And the rho here is in kilogram meter cube. Mass over volume. G, we're going to use a 9.8, right? And then actually here I'm going to emphasize something. Webworks is tricky in terms of number. So you need to make sure it's very precise because our tolerance is very small. So G here, we actually, for thermodynamics, I'm going to make a note for thermo Webwork problem. And this G, we're going to use 9.80665 meter per second square. Okay, pretty precise number here. So that's going to be the G. All right, and H here, in this problem, they are using millimeter. So if we were to change that millimeter to kilometer, so you're going to make sure here that's going to be 1 unit change divided by 1,000 because 1 meter is 1,000 millimeter. Okay, so doing that, if you were using those units, you're going to get a unit of Pascal because we have already proved rho GH. If you use the base unit, if you use the standard unit, you're going to get in Pascal. So here, be aware, your 65 here, it's in kilopascal. So you can do either two things. Since they ask you in unit of kilopascal, final answer, what I would suggest to do is change this Pascal you calculated to kilopascal. In order to do that, you're going to make sure you're going to divide by 1,000 again, right? So that's it. So watch out for that one. You have to change this Pascal to kilopascal in order to get the right answer. Then you will be able to have the same units here, or kilopascal. All right, so that's for this problem. I'll see you next time. Bye.